Okay, I'm not going to punish you all for being on time. So if anybody's got any questions, I'll open it up. As a reminder, right, I am recording this and I'll post it for people that couldn't be here today that are working. I know at least one person said they're working and couldn't be here. Again, you can ask questions in the chat. You can just send them to me at the bottom. If you go the 2-button little pull-down menu, you can pick who's ever in there to send a private message if you wanted, or certainly, open up your computer audio and ask away. But I have nothing planned per se, and so I will take questions. Anybody's got them?
I have one. Well, I have several, but we'll start with one. Okay, so I was reviewing my notes, and somewhere in one of your videos, you said that the elasticity of the arteries helps to maintain blood pressure during diastole. So I was just kind of struggling with that concept a little bit.
Okay, so think about it this way. The first thing, and this is true in a lot of scientific things, and if you take physics, this comes up again and again, and obviously in the many sections of physiology it does. We'll see the exact same concept in the respiratory system towards the end of the semester. But fluids, whether it's a gas or a liquid, move because of pressure differences, right? So our blood flows because of pressure differences. The pressure in the arterial side is greater than the pressure on the venous side, and that causes blood to move. So if you go back to the heart pressure, right, the ventricle, right, and we'll just stay with the left side. The same thing is true on the right side, just not to as great extent because it doesn't have as high a pressure. But during systole, right, the systolic pressure becomes on average 120, right? That pumps blood and moves blood out of the heart and into the aorta. Now, the aorta accepts that blood, right? And then the ventricle relaxes, and you get the, the semilunar valve, the aortic semilunar valve that closes and prevents blood from going back in the ventricle. But since the ventricle goes down to 0, right? If your aorta did the same thing, then blood would actually go backwards through the capillaries, right? Because it would have a lower pressure than the rest of the system. So what happens is the aorta and the large arteries, and as you get smaller and smaller arteries become less and less elastic, has this elasticity. And what it does, it allows it to accept that blood volume, stretch, and then sort of compress on that blood volume and keep the pressure higher. And so by keeping that pressure higher, it keeps the force for blood flow, that pressure difference, higher in the arterial tree and keeps blood moving. And so that's what it means by elasticity. As people get older, they lose some elasticity in their arteries, and they start to have issues with systolic pressure problems primarily. But because they can't accept the pressure by expanding, and so systolic pressure goes up significantly in some people. But it's the elasticity that helps to maintain that pressure head to keep blood flowing. And if you didn't have that, then either the systolic pressure would have to go really, really high, and then we would lose the ability to have the driving pressure for blood if we didn't have that elasticity. Does that make sense?
Yeah, so basically the aorta, if we're just sticking with the left ventricle and the aorta, the aorta always has about 80 millimeters of mercury as far as pressure in a healthy person. Is that?
Yeah, so the diastolic pressure is a measure of the minimum pressure during relaxation, right? So given that normal 120/80, yeah, that would be perfect to say that they're always going to have at least a minimum of 80 diastolic blood pressure during that time.
Okay.
All right, you said you had a couple. Keep going, and maybe that'll spur other people.
So another one is arterioles have the smallest cross-sectional area. So because the walls are really muscular, and so basically that that's saying the diameter, the amount of space the blood has to move through the arterioles is the smallest of all the different vessels. Is that correct?
Yeah. So it's like, even though, what's the best way to say it?
Like capillaries are super, super tiny. Somewhere in here you said they're only about the diameter of one red blood vessel or one red blood cell, which is really, really small, but somehow arterioles have a smaller
Cross-sectional area. Yeah. So it's like saying, pennies are the smallest unit of money that we have in the US, right? But you could have 10,000 pennies and you'd have more money than if you had 50 dimes. And so the idea is, even though the arterioles have a larger diameter, if you add all of them, those diameters up, the total cross-sectional area, then it's going to be a lot less than a capillary. And so that means that the arterioles are our greatest site of resistance, which means they're the place where we can change blood flow the most, because that's your weakest link, if you want to think about it that way.
Okay, so it's the arterioles have the smallest total cross-sectional area, not just like one arteriole's cross-sectional area is smaller than one capillaries. It's the total number of arterioles versus the total number of capillaries.
Yeah, and if you look at it in terms of raw numbers, right? Yeah. I've read that capillaries have a total cross-sectional area, or maybe a better way to say it is a total length of like 50,000 miles in the body.
Yeah.
Right, and that's so there's 60,000 miles total of blood vessels, and 5/6 of it belong to capillaries. So yeah, they're really, really narrow, but there's a whole bunch of them, and that makes up for the narrowness, and that's why the arterioles, one arteriole can go to literally 1,000 capillaries.
Yeah. Okay, that makes sense. The fact that it's like the total of all the arterioles versus the capillaries. Okay, and so this next part might be a little bit different. So it's the arterioles are the greatest site of resistance, and that's because that's where we can change the radius.
Well, it's kind of the vice versa. Because they're the least total cross-sectional area, they have the greatest resistance. So that's like, once you get past an arteriole, then it's easy to go into a capillary because there's so many of them, right? So it's sort of like going across the bridge into the city, right?
Okay.
That's where the traffic backs up, because that's where it's most narrow total cross-sectional area, right? And once you get into the city, there's a whole bunch of streets you can go on, right? So that's kind of the weak link. And so that's why I think, from an evolutionary point of view, and I've never studied this part of it that way, but I would think from an evolutionary point of view, that's why we developed more muscles in the arterioles, so we can change their diameter, which then allows us to dictate blood flow to a much greater degree than any place else in the body.
Okay. So the arterioles, we can control the blood flow there because the number of arterioles connects to so many capillaries, so we can kind of like close off some to reroute the blood flow to the areas that it needs. Is that
exactly?
Okay.
Exactly.
All right. So another question that I had was mean arterial pressure. I think you said in a video is decreased through the system because of resistance.
Yes.
Okay. Can you explain that a little? Mean arterial pressure is kind of.
Okay. So, and this is not, it's not just mean arterial pressure, but it would be any pressure, right?
Okay.
So as an example,
is this the greater the resistance, the
greater the length of the tube, the greater the resistance.
Okay.
All right. So, so mean arterial pressure, right, decreases from your arterial side to your venous side because of that resistance, because of basically a couple things: the viscosity of the fluid, the diameter of the blood vessels gets smaller, and the length the blood vessels have to travel to get to the end. So all of those things decrease mean arterial pressure over time.
Okay, and that's because it increases resistance?
Yes, because of the increased resistance.
Okay. If someone else has questions, please feel free to ask. I made a list before I got on here, so.
Oh, I just wanted to know if will you be reviewing the laboratory exam?
I was not planning on, but we could talk about it.
Because I don't, hold on, let me go see it again, because I don't know if, honestly, I should have checked that maybe before coming here, but last time you didn't post the answers for it, like which ones we got wrong.
You should be able to see it now.
Oh, okay.
Yeah, so check to see if you can see it, and if you still can't, let me know. But I have to unmask it in 2 ways, and I didn't know that the first time. So I unmasked it one way, but you guys still couldn't see it. So I have to go in and hit another button to do that. But I think you can now. Anybody can confirm that? Have you gone back and looked and reviewed your lab quiz?
Yeah, I've seen it. I actually have a question on one of them. It's the venous pressure one.
Okay.
I was doing calculations and I wasn't able to get the answer.
Oh,
So-
yeah, me either.
So for the venous pressure one, all we care about is how high the vein collapses above the heart, right? The measurement was from the right atrium, which is the heart height, to when it collapses. So I think that's what I forget the exact number. I think it was 93. So if you take 93 and divide by 13.6, then you get that answer that's like, I don't know what, 5-ish or something.
Oh, so it was just the 93 then.
Yeah, because we don't care how far below the heart it was. We never measured that. So it's the 93 divided by 13.6, which was what, 6.8, or I think.
Oh, okay.
Can you go on over question number 13? I thought I had that one right. We just had to calculate the mean arterial pressure. I did it like twice. I don't know why I got it wrong.
What were the numbers, do you know?
It says 130 over 100, given the pulse pressure. Yeah, it was just calculate the mean arterial pressure.
So the mean arterial pressure would be 110 in that case. Does that make sense? Because you take the pulse pressure, which is the difference between 130 and 100, right?
Mm-hmm.
And that equals 30. And then you multiply that by 1/3, which is 10, right? And then you add that back to the 100, that's the diastolic. So 1/3 pulse pressure plus diastolic is mean arterial pressure. Pulse pressure is 30, 1/3 of 30 is 10. 10 plus 100 is 110. That's what should be keyed at, that's the question.
Okay. I don't know why I got 85.
Well, you look at it this way: if the number is 130 over 100, right? It has to be between those two numbers, right?
Mm-hmm.
You can't have a mean arterial pressure greater or less than that. So 85, would be incorrect just from looking at it. It has to be between those two numbers, systolic and diastolic. Did you? Maybe you took 1/3 of something and added it. I don't know. Yeah. Well, if you took the 1/3 systolic of 130, 1/3 of 130 on top of my head would be what, 43.3, and 2/3 of 100 would be 67 point something, 67.7. And if you add those two together, it'd be 110 as well. So the 1/3 systolic plus 2/3 diastolic would be 43.3 plus 67.7, which would also give you 110.
Okay. Can you go over the Starling forces problems? I think it's number 15.
So people got different Starling force problems, and the one was just keyed wrong. I changed one of the answers and flip-flopped 2 of the numbers, but I never changed the answer choices. So the one was actually, some people got it where it actually came out to -22, right? And some other people got the one where I flip-flopped the numbers and it came out to -20. but I never changed the key. And everybody I checked that got that put negative 22 anyway. So if you calculated negative 20 and said, oh, crap, that's not the right answer, I don't see it there, but negative 22 is the closest, so I'll put it, which everybody did, then you got it correct. But the actual real answer for that one was negative 20. And it just depends on which question you got.
Mm.
Anything else about the lab quiz? Oh, the other one that a few people emailed me about, so I'll mention as well. Most people, and I'm not going to say literally everyone, but close to everyone, got the first little essay question right? So was it 3,800 white blood cells is below 5,000, so the person has leukopenia, and basically you need to talk about their immunocompromised, right? They're going to get sick more or something like that. And most people did a really good job explaining that one. The other one about the premature babies and jaundice was actually a question right out of 6.1 in the back of Fox. And it was not looking at the RH incompatibilities and erythroblastosis fetalis or hemolytic disease of the newborn. It was actually looking at why do premature infants especially have jaundice. And basically the answer was it's the liver that processes the bilirubin. And since premature babies have an immature liver, a liver that's not fully developed or not functioning, that was part of the answer. And that was worth a point, basically. Then they would have jaundice. So a lot of people, came up with a decent idea. So the people that talked about RH incompatibilities and never mentioned an immature liver got 1 point. And the people that talked about the liver processing the bilirubin and it was immature in the premature infant got 2. So that was kind of the difference if you lost one there.
Oh, I got that one right.
Oh, okay, well, see, they're good.
Not me. Can you
Anybody else?
explain, no, not about the lab, but the lecture for tomorrow? I'm having a little bit of trouble of understanding the cardiac cycle, which valves are closed and open and.
Okay,
Yeah.
so we'll look at that in 1 sec.
Okay.
Before I leave the lab quiz, anybody got any questions? Any other questions about the lab quiz?
I have one actually.
Okay.
So when I was calculating the equation for NFP,
Uh-huh.
I wrote on my notes that it's always positive, but then when I did it on the lab quiz, it came out to -10, which I chose that answer and got it right, but I don't know what does it mean if it is a negative number?
So for the NFP, and we'll see that at the arterial end of a capillary, the NFP is going to be positive, okay? So it's always positive at the arterial end, but sort of dovetailed on Jess's question a couple minutes ago, is as the blood goes through the capillary, it meets resistance from the walls of the capillary, and so the pressure goes down, and actually there's the 4 forces that determine whether or not fluid leaves a capillary or comes back into a capillary. So at the arterial end, the forces have a net positive, that's why it's called net filtration pressure, a net positive effect, and so fluid leaves the capillary, we call that filtration. At the venous end of the capillary, because of those pressure differences is sort of flip-flopped, blood has lost its plasma, the fluid that's been filtered out in the first 2/3 of the capillary. So there's less fluid pressure in the capillary, so that goes down. Plus there's less pressure anyway because of the resistance. That effectively increases the proteins that are stuck in the capillary, because generally they don't leave across the wall of the capillary. So that tends to have a effect to pull fluid back in. So at the venous end of the capillary, it's negative, and that means you favor reabsorption. So as an example, had this been a lab quiz we took in class, I probably would have given you that question and then said, based on your answer, which was -10, I would have asked, what end of the capillary are we at, the venous end or the arterial end? And you say, oh, because it's negative, that favors reabsorption, and we're at the venous end. And if it was positive, that would favor filtration, and that would be at the positive end. So It's always positive at the arterial end and almost always negative at the venous end.
Okay, thank you.
Could you
Sure.
repeat it one more time? Sorry about that.
About the positive negative?
Yeah.
So net filtration pressure, right? You figure it out by those 4 values. So the pressure of the hydrostatic pressure within the capillary, the osmotic or oncotic pressure, the pressure due to dissolved proteins in the capillary, the pressure of proteins outside the capillary, and the pressure of the fluid outside the capillary. So that equation for net filtration pressure takes the 2 positive pressures that tend to push or pull fluid out of the capillary, and then subtract from that the 2 pressures that tend to push fluid or pull fluid back into the capillary. And those numbers are positive at the arterial end. When we first enter a capillary, there's a net filtration. We push fluid out. But at the venous end, as we move towards the other end of the capillary, it pulls some fluid back in. And so it's designed to do that. And what happens is that always leaves a little bit of interstitial fluid in the capillaries, from the capillary plasma to become interstitial fluid. And that helps to bathe the cells. And then that's going to be picked up by the lymphatic system in most areas. And from that, that's going to go through the lymph system and cleanse the blood and then dump it back into the subclavian veins later on. So if you see a positive number for NFP, it means it favors filtration, and that means it's towards the arterial end typically. If you see a negative number for NFP, that means it favors reabsorption, and that's going to be at the venous end of the capillary. And we're going to see some of these ideas again in the kidney, when we talk about the kidney and glomerular filtration rate, which is determined by the Starling forces. And that's one of the reasons I said, make sure you get it down, and not only will it help you on the lab quiz, but it's going to help make it easier when you look at that stuff, you know, starting later on this week, probably for the kidney lectures. Good?
Yes, got it. Thank you.
Any follow-ups for lab quiz before we go on to cardiac cycle questions? All right, so just the cardiac cycle, the questions about the valves, let's talk about the whole thing and just go through it. Let's see. I think I can do this. So here's the cardiac cycle stuff, and I'll just, you know, leave it right here so we can manipulate it pretty easily. When we look at the cardiac cycle, we can start theoretically anywhere because it's a cycle and it's always going to come back around. But the cardiac cycle sort of determines basically when we have filling and when we have ejection of blood, and then the times when we don't have any change in volume of blood, okay? And so it's pretty easy to kind of think about, if you think about the names, they're usually named correctly in terms of where the blood's going, meaning that it doesn't tell you everything about it. Certainly they're named correctly, but it doesn't tell you everything about it, but it tells you something. And so by convention, the cardiac cycle is divided up into 5 phases. And the first phase, you know, is more often than not called late ventricular diastole, okay? And so when we look at late ventricular diastole, what's happening is that our goal is to fill the ventricles, right? And so this is towards the end of the ventricles relaxing. In addition, while it's not part of the name, the atria are relaxing as well. So we also have atrial relaxation. So if the goal is to fill the ventricles in the cycle.
I like that one. No, give him, get some for Michael and give him a different one. I like.
So the goal is to fill the ventricles. right? And what you can do, then if I'm trying to fill the ventricles, it means that the AV valves, the atrioventricular valves, have to be open. So blood can go from the atria to the ventricles. And there's never a case in the heart where all four valves, both sets of valves, would be closed. I'm sorry, open. So there's never a case where they're all open. Because if they were, then you would put blood in the ventricle and that would just go out the other end. And when the ventricles are filling, right, the valves from the atria to the ventricle are open. So both AV valves are open, and both semilunar valves, those are the exits of the ventricles, the aortic and the pulmonic semilunar valves, they're closed, okay? And this actually results in about 2/3 of the ventricular filling. So about 2/3 of the blood that fills the ventricle, right, comes from this. And if you kind of go back to some of the numbers we talked about, remember there's always a amount of blood left in the ventricle after ejection. It was called the end systolic volume. That was about 30 mils, which means the ventricles have to fill about 70 mils. And so of that 70 mils, somewhere in the neighborhood of about 45 or so of the blood comes from that passive filling in the first phase or stage of the cardiac cycle called late ventricular diastole. Okay? Most of your cardiac cycle is spent in this phase. Okay? And that's why we say when we calculate mean arterial pressure, 1/3 systolic plus 2/3 diastolic at rest, right? That's, to kind of talk about this. So once we get past this phase, we go to the second phase, which is atrial systole. Now, atrial systole is just exactly what it says, atria, right? Systole means contraction. So it's when the atria contract. And so what happens is the atria contract and push 1/3 of the blood, that last 1/3, 25, 30 mils at the most, probably, maybe even 15 or 20 mils only, pushes that last 1/3 of blood into the ventricle. To do that, right, you have to have those AV valves open still, and the semilunar valves still have to be closed so that you can fill the ventricle, okay? So that's atrial systole. And remember, just to kind of connect it to the conduction cycle, what caused atrial systole, what caused the atria contract, was the SA node fired, and that caused the atria to get electricity. That electricity causes contraction. So as the atria are pushing blood into the ventricles, the AV node is picking up that electricity and sending it down the bundle of His and the left and right bundle branches. Those are going to those Purkinje fibers. And now that electricity is now at the bottom of the ventricle, okay? And so now the ventricle starts to contract. And that's called isovolemic ventricular systole or isovolemic ventricular contraction. Whatever you want to call it, that's whether it's systole or contraction, it means the same thing, so either one's fine. So when you see the word isovolemic, right? Iso, I think most of you now realize it means the same. Volemic sounds like volume, that's because it is. And some people spell volemic with an E and not a U. I see it both ways, but that's somewhat irrelevant. But isovolemic ventricular systole means that the ventricle is not changing volume, okay? And since the ventricle is not changing volume, that means there's no blood coming in or no blood going out. And to do that, all your valves have to be closed, right? So during isovolemic contraction or relaxation, we'll see later, it's the only place where all four valves are closed in the heart, right? So all four valves are closed in the heart during the isovolemic stage. And the reason why they're closed is, and again, we'll stay with the left ventricle because that's the numbers we know pretty well. In order to eject blood, going back to that thing I said at the very beginning, blood moves because of pressure differences. So I have to have a higher pressure in my left ventricle than my aorta for blood to move. And so blood's not going to be ejected out of the ventricle until that blood pressure in the ventricle exceeds the diastolic blood pressure in the aorta, which we know is about 80 if you have normal blood pressure, right? Because 120 is systolic, 80 is diastolic. So I have to get over 80 to eject blood.
Is that also the afterload?
So that would be considered an estimate of the afterload, absolutely.
Okay.
So the higher the afterload, the higher diastolic blood pressure you're gonna get. It's not exactly the same thing, but for our purposes, you consider it exactly the same thing.
Okay.
Yeah, but it's a great estimate of it. So the higher the afterload, right? And this is why, you know, diastolic hypertension is so bad, is the higher the afterload you have to overcome to eject blood, the heart has to work harder. And, you know, that becomes pathologically bad if that afterload is too high, if you have hypertension. So it weakens the heart because the heart has to get enlarged to do that. And when your heart enlarges in that way, it actually becomes weaker. And that's what heart failure is, or scientifically or medically called cardiomyopathy. But this is when we have this isovolemic ventricular systole happen. Now it's isovolemic on the other side, because remember, if you go back to those pressures of the atria, they're like 5/0, right? And the atria just did the atrial systole, so they contracted and pushed most of the blood they had into the ventricle. So now they're relaxed without pretty much any blood in it, so their pressure goes down to 0. And so once the ventricle starts to generate pressure, the AV valves close off because the pressure of the ventricle is greater than the pressure of the atria, so those are closed. And because the pressure of the ventricle is not yet higher than the pressure of the aorta of the pulmonary trunk on the right side, then the semilunar valves close. So during the isovolemic phases, we have all the valves closed. So that's the third phase. The fourth phase is called ventricular ejection. And, yeah, go ahead.
So in this time after the ventricular ejection, would that be the end systolic or end diastolic? That's what I'm confused.
So so before ventricular ejection, right? So at the end of isovolemic ventricular contraction, right? That's my end diastolic volume.
Okay, so isoventricular.
Yeah.
Okay.
And it's the same volume at the end of atrial systole, right? Because the volume hasn't changed by definition into the next phase. So at the beginning of ventricular ejection, this is all the blood we're going to have in the ventricle for this contraction, right? So that's what we call end diastolic volume. That's the biggest one.
Okay.
Okay. And so now that wave of contraction that got passed through the conduction system I mentioned a couple of minutes ago, now that's going up from the bottom of the ventricle and squeezing the ventricular muscle. And that pushes blood out of the heart. And once remember during the isovolemic ventricular contraction, the ventricle is actually contracting. So the muscles are shortening, which means the size of the ventricular chamber is getting smaller, okay? And so as we get the chamber size smaller and smaller and have the same volume of blood, the pressure goes higher and higher in there. And since the pressure gets eventually above the diastolic blood pressure, then we eject blood. And that blood we eject would go out in the aorta or in the right side of the pulmonary trunk. And that pressure would be equal to whatever pressure the ventricle generated. That would be our systolic blood pressure. So that's the peak pressure of the ventricle in normal people. If you had a valvular issue, it wouldn't be the same. But if your blood pressure is 120 and normally, and you have a normal heart, then your ventricular pressure would also be 120. And so obviously to eject blood out of the ventricle, right? You think, okay, I'm injecting blood. That means that the semilunar valves have to be open so I can move blood from the ventricle to the aorta or to the pulmonary trunk. But the AV valves have to be closed, otherwise blood would go back in the atria. We don't want that, right? So we have, again, that example of, we got two individual valves open, the semilunar valves, and we have two individual valves, one set, the AV valves that are closed. Once we get through that, we have the isovolemic ventricular diastole or relaxation. So now the ventricle starts to relax. And so as the pressure gets less than systolic pressure, and that part of that is that elasticity we talked about at the beginning, that pressure is maintained because of the elastic fibers. And so once we do that, blood actually starts to go backwards a little bit from the aorta into the left ventricle. We don't want to do that, so we have those pocket valves, those semilunar valves that close up. Okay, so once those close, that's the beginning of isovolemic ventricular diastole or relaxation. And as the ventricle relaxes, it's still got a little bit of blood in it, about 30 mils on average in a normal person, right? It's not until the pressure of the ventricle gets less than the pressure of the atria where we open that valve again and start back into phase one, the late ventricular diastole. So that's why it's called late ventricular diastole, because we have two parts to diastole. The isovolemic part, where the heart is relaxing but not changing volume because all four valves are closed. And once one set of valves opens, the AV valves, then we're back to late ventricular diastole in the filling.
Can I ask about end systolic volume? Why does the heart leave about 30 milliliters of blood in the ventricle at the end of contraction?
It's a good question, and most scientists that looked at this have theorized that it's easier to put
to make pumping blood smoother, kind of like, because I mean, in theory, there's never a time when we don't have blood going through our heart in some capacity, right?
Yeah, there's always some sort of blood in there, but it takes a lot less energy to put a little more blood in and spit 70% of it out than to put less blood in and spit all 100% out, right?
That's what I'm thinking. It's like it's more efficient to spit some of the blood but not all, but keep a little reservoir just to kind of like make the contraction and the moving of blood, I guess.
Yeah, it's like trying to get the last bit of peanut butter out of the jar, right? Sometimes it's just not worth it.
Yeah. Okay.
So you just go, okay, I'm just going to get a new one. And that's basically what a heart does. So other people have talked about some other things like, why do we have what is it? The trabeculate carneae, those rigid cage-like muscle structures at the bottom of the ventricles. That has something probably to do with it. And so maybe, there's a reason why we do that, but it just seemed from if you look at the physics of it and the energy required to eject all the blood versus the energy required to eject some of the blood, it's a little effort to do some of the blood. It's a lot of effort to do all the blood. So it's not worth the effort. Yeah.
Okay. Thanks. It was just, I can accept the fact that we still have 30 mils, and that's end systolic volume, but I just was really wanting to know why.
Yeah. So that's probably the reason why, obviously.
Okay.
So when it's late ventricular diastole and atrial systole, the AV valves open when 2/3 goes in and 1/3. They're both AV valves open. Okay.
If we're moving blood from the atria to the ventricles, those valves have to be open, right?
Okay, so it goes 2/3 first, and then 1/3 is it's left in
Yeah, so 1/3 is that when we actually contract it.
Okay.
Just it's like the atrial systole, which is the second phase of the cardiac cycle. It's like that final push.
Yes.
Oh, okay.
Does that help?
So 2/3 goes in from the atrium to the ventricle, and then another 1/3 goes in from the atrium to the ventricle.
Yeah. So the first 2/3 are it's like passively flowing.
Okay.
Flowing through, and then that last 1/3, it's like there's not enough momentum to kind of let it just pass. So it has to give it a push to get it.
Okay, I get it. So the AV valve is open when they both happen, right? At the same time?
Yes.
It's just flowing and then boom, and then it just hits, final kick, just pushes it. Okay.
Mm-hmm.
Okay.
Like washing your car. You can hose it off and get a lot of the dirt off, but to really get it clean, you have to get a brush and scrub it, right? It's the same thing. We can move some of the blood in, but to get that last bit of blood we need, we have to actually contract the atria and spit it out. If you didn't have functional atria, you would still be alive. You just wouldn't work nearly as efficiently as you do now.
Yeah. Can I also ask about it's probably not that complicated, but I don't know why I'm confused about this, but the events of the cardiac cycle of the waves, like the P wave, QRS complex, and T wave, like the repolarization, depolarization of it.
Mm-hmm.
Can you kind of go over that real quick, please?
So okay, I'm going to do it, and I'm going to, because you asked, I'll tell you something. All right. I asked about it on the lab quiz, right?
Yeah.
Because I wasn't going to ask about it in lecture.
Oh, okay.
All right. So there's a
Okay,
little.
never mind.
That's your bonus for showing up today.
Oh,
But
Yay.
the P wave, right, corresponds to the atrial depolarization, the electricity going through the atria. The QRS complex is the atrial repolarization, but the primary thing that happens that we're concerned about is ventricular depolarization, because that leads to ventricular contraction. And then the T wave is ventricular repolarization, resetting.
okay.
Yeah, but I
So
wasn't
it's
going to
kind
ask
of
that.
like the action potential, where like, you know how it goes up to depolarize and repolarize and hyper. It's kind of like
Exactly.
that. Like,
Yep.
okay.
Yeah, exactly. So you have to, every time for the action potential you did depolarize, you had to do what? Repolarize afterwards. And each one of
Yeah.
the waves is looking at the electricity of the heart. So yeah, it's
Okay.
slightly different, but the exact same idea.
Okay. That's what I thought. Thank you.
I have a question. Could you please go over just really briefly the vessels?
Sure. Let's do this. So for the vessels, we're going to worry about, instead of 5 sets like you would in anatomy, because functionally the veins and venules are the same thing for the most part. Structurally, they're a little different, but for the most part, that you can group them together functionally. So we'll just worry about 4 sets of vessels: the arteries, the arterioles, the capillaries, and the venules and veins together. Okay. So the major characteristics of arteries is they are muscular, because they do help determine blood flow a little bit, but they're also very elastic. That's their big thing. And again, that's so they can maintain pressure during diastole. Most of the arteries in the human body generally have a high oxygen content. The exceptions in adult humans would be the pulmonary artery and vein, or flip-flop, or in the fetal circulation, the umbilical artery and vein, or flip-flop. But every other case, the artery should have more oxygen than the vein, because that's bringing blood to the tissue, and the vein is removing blood away from tissue. Arteries tend to have low volume. It's not on the chart, but it's like 10% of the blood volume or less is in the arteries. By definition, arteries take blood away from the heart. All right. And then they have what's called a divergent flow pattern. So that means that one artery branches into 2 arteries or smaller vessels, which then further branch. So they are diverging. And again, their main job is to maintain the driving pressure for blood when the heart is relaxed. So that's arteries. Arterioles are much thinner and have a very large muscular layer comparatively. And that's because their job is to partition blood flow, which means we can send blood away from our guts to our muscles and vice versa. So maybe when we're done here, you said, okay, I'm going to go out and go for a run or something. And so right now, maybe you ate first before you came online. So you've got a lot of blood flow going to your guts to digest the food that you have and to take that energy out and all those different things. But now when you go for a run, you want to take that blood away from your gut and put it into your working muscles. And so the way we do that is by partitioning blood flow primarily through arterial constriction. So the arterioles constrict, and then when you're running, the local metabolites in your muscles that are working, right, cause dilation, and that increases the blood flow to the areas of need. So that's one of the major ways we partition blood flow. As we talked about at the very beginning, some of you weren't here yet, I don't think. The arterioles are also the highest site of resistance, and that's because they have the smallest total cross-sectional area. So even though an individual arteriole is wider across than an individual capillary, you have so few of them that when you add up all that cross-sectional area, it's not very much. While capillaries, even though they're the smallest, you have a whole lot of them. So it's like somebody saying, all right, I'll give you, 10 quarters or a million pennies. You can say, well, I don't really want a million pennies, but it's worth a lot more money, so I'll deal with it. So since even though they're smaller, you have so many more of them, they're worth so much value. And that's the same thing for the arterioles versus the capillaries. The diameter of the arterioles is controlled by a couple things. And we saw that when we looked at the homeostatic control of mean arterial pressure, right? There's that sympathetic only tone that's always there, right? So it goes back to Canon's postulates. You have tonic activity, and that sympathetic tone is called the vasomotor tone. And it's pretty easy. If you increase that sympathetic stimulation, they constrict, and if you decrease it, they dilate. And so you always have some sort of tone there, right? And that means that we can always send less action potentials and get more and more dilation if we need to. It's never completely off, because if it was completely off, then you couldn't dilate it anymore. They're also regulated not just by the sympathetic system, but hormones. We talked about epinephrine, right, being a sympathomimetic a little bit.
Sorry
Yeah.
to interrupt you. That's what I had a question about, like the arterioles, the diameter, the vasomotor tone. So I think I was also confused about that previously. I don't understand that part. Like, so there's always a little bit of tonic control, you said, through the sympathetic?
Yeah, so remember, the blood vessels are the major way which we control resistance, right? And especially the arterioles, to maintain mean arterial pressure, right?
Mm.
And so since they are one of the mechanisms we use to do that, we need to have antagonistic control, meaning we need the ability to constrict or dilate a blood vessel. And since there's only sympathetic branches of the ANS that go to blood vessels, we don't have that antagonistic control like we do with your heart, right? So when we talk about your heart, you want to increase your heart rate, you can either increase the sympathetic or decrease the parasympathetic, right? But we don't have that in the blood vessels because we only have sympathetic. So if I want to dilate a blood vessel, right, and the sympathetic wasn't on, there's no way to dilate it. So you have to have a constant a number of action potentials coming from the sympathetic system to blood vessels. And then I can change that number. It's like having a radio that's always on. You can never turn it off, but you can change the volume. And so if you don't really want to listen to it, you can turn the volume almost to off, right? And you won't even hear it, probably. But if you want to listen to it really loud, you can crank it way up. Well, our blood vessels can do the same thing. And if we really want to constrict them, we can send a whole bunch of sympathetic, a barrage of sympathetic activity to constrict blood vessels. But if we want them to dilate, we can reduce that sympathetic activity and then get them to widen, which would then obviously help blood flow go to those areas where we need them most. The problem is we don't have the ability to individually say, oh, I want to send more sympathetic stimulation to my legs because I'm running and less to my gut. We don't have that ability. We can change the sympathetic system, but we don't have the ability to differentiate it, to go, oh, we're only stimulate the heart with the sympathetic, not the blood vessels or not the guts. And so that's the problem. So we need these local controls to fine tune what we're trying to do, and the hormones.
So the local controls and you said the little analogy of the little radio present, that would be the most vasomotor tone, like always present, like acting as the tonic control?
Yes, exactly.
All right.
Yep. And then there's hormones, right, that control it, right? And just while we're at it, all of the known hormones that affect the diameter of an arteriole, right? All of the hormones cause constriction that we've ever found.
Okay.
So epinephrine, norepinephrine, oxytocin, antidiuretic hormone, which is also known as vasopressin, and angiotensin 2 are all examples of things that would cause constriction, hormones that would cause constriction. On the converse side, all of the local chemicals, potassium, lactate, lactic acid, lactate itself, hydrogen ion, CO2, adenosine, histamine. All of those local chemicals cause dilation. And so, make sure you understand that difference in those. For the capillaries, they're the thin wall. They're just simple squamous epithelium. They're very narrow, but there's very, very numerous. Again, I've seen, I don't know where they come up with these numbers, but if you look at the blood vessels, if they were laid end to end, your arteries, arterioles, venules, and veins would be about 10,000 miles, and your capillaries would make about 50,000 miles. So there's lots and lots of capillaries, and they have by far the largest cross-sectional area of all vessels, which means that when blood gets to a capillary, the actual blood movement, velocity of blood flow through the capillary slows down. And we believe that's to help enhance the time for exchange, right? The slower they move across, the more time you have to exchange blood there. And so that's the capillaries, and the fluid exchange is dictated by those startling forces that we'll see again when we look at filtration in the kidney. And venules and veins, a couple things about those. They're said to be a high capacitance. It means they have a high capacity to store things. And that's because they're very floppy. They have convergent flow. So eventually all your blood vessels go back to, in terms of most of your body, either the superior or inferior vena cava that leads back to the heart, right? So those are the largest veins. And so everything converges onto those. You have two sets of veins. You have one that's close to the surface, and you have one that's deeper typically. While you only have one typical artery that goes to an area, you often have two veins. And that's so we can dissipate heat if we need to, or retain heat if we're in a cold environment. So we can differentially send blood flow to the veins on the surface if we want to dissipate heat. Like if you're outside today, it's pretty warm, and especially compared to what it's been, up until this week. So you would have a lot of blood flow going to your skin to try to dissipate heat to the environment. So, we can change blood flow there. And then again, sort of opposite arteries, right? They return blood to the heart, so they generally have the lower oxygen. The exceptions are the ones we mentioned for the arteries, the pulmonary artery and vein, and then the umbilical artery and vein. So your veins also help regulate body temperature. It's where the vast majority of your blood is stored. Usually 60, even 70% of your blood sits there. And if you constrict blood vessels, it increases venous return back to the heart. And so that's called venoconstriction particularly. And so don't confuse venoconstriction, which is specifically to veins, with vasoconstriction, which generally is specific to arterioles. Vasoconstriction is going to decrease blood flow because you've increased resistance. Venoconstriction is going to increase blood flow because you increase venous return to the heart. So any follow-ups for that?
I think somebody asked if you were gonna post this.
Yeah, I see it. Yeah, it's recording, I think, I hope. Yeah, it's recording. So last time it took a while. So I'm trying to record it differently. I hope it works. I had it record off-site, and for the one we did before the lab quiz, and I didn't get the link for it until that night really late, and I forgot to post. I posted on YouTube, but I never posted it that I posted on YouTube. So a couple people looked at it because it had a couple of views, but this one I'm doing locally. So hopefully this recording should be available fairly soon after, because it still has to render, and then I'll upload it to YouTube, and then I'll make an announcement for everybody if you guys want to go back and refer to it, or if somebody couldn't be here, because I know at least one person emailed me and said, oh, I got to work, and so I've sort of already announced the time. So yeah, so my goal is to post it.
Okay, I have another question.
Yeah.
Can you go over and differentiate what the difference with pressure and the difference of resistance or total peripheral resistance is?
Okay, so it depends on what frame of reference we're talking about? And are we talking about the direct effect or a compensation effect? So,
Okay, I think I'm really just struggling with mean arterial pressure, kind of this whole section about like blood flow, pressure, resistance, and then how that plays into how that
Okay.
affects mean arterial pressure. And so I don't know.
okay, so
The words just all sound the same.
let's go
or-
way back to the very beginning, where pressure, right, equals flow times resistance.
Okay.
Right? Now, if you look at them with letters, right, pressure, we use a capital P,
Yeah.
equals flow. Because scientists don't like to use F for variables, because like F is function and for other things, they use Q, which is a problem because we use Q for a lot of things. And if you think back, you know, earlier this semester, we used the Q for Q10 effect in enzymes. We mentioned that. But so that's Q. And then resistance was a capital R, right?
Mhm.
So if you remember pressure begins with a P, then you just go in order, P, Q, R. So pressure equals flow times resistance, right?
Okay.
So if we apply that to mean arterial pressure, right?
Just to clarify really quick, flow is volume of blood or speed of blood?
Volume of blood, so volume of blood per unit time.
Okay, so it's kind of a combination of the two.
Yeah, so it's volume, so it's mLs per minute is the units for that, mLs per minute.
I have a question. So when we did the formula for the resistance, and I remember you were explaining with the straw and stuff, and then you kind of like flipped it at the bottom.
Mm-hmm.
When it was flow, which is Q, it was pressure over resistance, and then we did the
Well,
I can't say his name. Postiel.
Postiel,
You put pressure times radius over length and viscosity, right? But why is pressure again? I know you said that radius was gonna be on top because it was proportionally inverse. I can't say that. So but why is the P times radius if it's pressure over resistance, and then again pressure times radius?
Okay, so let's look at this. So looking at this, and we'll just really look at this bottom part, right? So pressure equals flow times resistance, right?
Mm-hmm.
If we want to look at flow, right, we have to do a little math, right? And so if I want to isolate flow on the right side by itself, if I divide both sides by resistance, right? So if I get resistance over resistance on the right side, that's going to cancel each other out because that's 1. And so I have to put resistance on the bottom of the other side. So I get flow equals pressure over resistance, right? So make sure you understand, right, that pressure equals flow times resistance, but flow equals pressure divided by resistance, okay? So when we look at Postiel's law, right, Postiel's law says resistance is equal to 8L times N over small r to the 4th. So don't worry about the 8, right? It's just a coefficient, but it's length times the viscosity. Since they're on the top, if we increase length, we increase the resistance because there's more friction on the walls of the tube. Remember, Postiel's law only refers to fluids moving through a tube, but there's more friction on the walls of the tube, which then increases the resistance, all right? And is the viscosity, right? So that's the thicker it is, right? So let's kind of look at, again, a thought experiment, right? So if you could go into a restaurant and sit down and eat and drink, right? Let's say that you got a soda, and then for some reason decided, I'm gonna get 10 straws, stick them end to end, stick the soda on the floor, sit in the chair at my table, and drink the soda. Is that going to be easier or harder to get the soda into your mouth with one straw versus a combination of 10?
It's gonna be
Harder, right? Why is it harder? Because there's greater resistance.
Wait,
Okay.
what do you?
You got a question?
Yeah, like how you mean like put all the straws and then just drink from it, or like?
So instead of having a straw that's what, 10 inches long, you've got 10 straws that's stuck together that's 80 inches long.
Oh, okay, got it.
Right? So you've got this 80-inch long straw thing that you're going to stand up and drink. And because it's such a long length, it's got to overcome great resistance. You probably can't drink it once it gets long enough. You won't be able to generate enough pressure to be able to drink if it's too long, right? So the length does affect the resistance. So we can't ignore that, but it does. The N, that handwriting N thing, is viscosity. They don't like to use V because that's like velocity and things in science. So they use that weird N. It's the Greek letter N. So that's viscosity. Viscosity is basically the thickness. So again, go back to you're still at the restaurant. You say, okay, I'm going to buy a shake, right? So you get a shake and you get a soda. And now you go, okay, I can't use the long straw. So my straws have to be the same length, right? And so then you drink the soda and drink the shake, which is harder.
The shake.
The shake.
Because it's got more thickness. It's got a higher viscosity. And so if the viscosity goes up, resistance goes up, okay? But on the bottom part is the radius. Now we can't use big R for radius because it's already resistance, as you can see over here, right? Big R is resistance. So little r is radius. Radius is related to diameter, right? If you look, and over here at the bottom, you can see, we have those little, stirring straws, right? So if you decided to take a normal straw and cut it to the same length, because we know they have to be the same length, and then tried to drink from this little straw with a small radius, or normal straw with a bigger radius, which is easier?
Normal radius.
Normal radius, right? And that's because as the radius goes up, the resistance goes down. So it's on the bottom, so that's inversely proportional, okay? What makes this also, so important physiologically are two other things, okay? If we look at the blood vessels, right? Can you change the length of a blood vessel?
No.
Not really, right? You know what? If you gain 10 pounds during this isolation thing because you're not doing anything and all you're doing is sitting and eating, right, or something, then yeah, you know what? You might actually gain a little bit of length in your blood vessels to help the the capillaries within the fat cells, right? And that might increase your blood pressure overall. Possible. But really, you can't appreciably change length very much effectively. Viscosity of the blood is determined by a couple things, but those things are controlled by completely different mechanisms. So viscosity is controlled by things like so what's the protein that controls viscosity? In your blood? Very nice. All right. So albumin, right? And that's more than half of your protein. So the amount of albumin you have determines your viscosity. The number of red blood cells you have determines your viscosity. And the relative amount of plasma you have determines your viscosity. Those are the big effects. So we can't change viscosity much because of that. So hang on a sec. I'll turn off my mic for a sec. I'm good. I just got I just coughed and I didn't want to cough in your ear. So going back to the screen. So viscosity, we can't ignore it, but we can't control it. And you just can't all of a sudden, decide, oh, you know what, I need to increase the viscosity of my blood because the pressure's not high enough. So I have to, pee out more, a liter of fluid or something. Yeah, it's affected by it, but we can't control it. So the only thing we can really control, especially in short term, is the radius. And so that's important physiologically. The other thing that makes the radius even more important is that it's raised to the fourth power in terms of Poiseuille's law, which tells us small changes in radius, right, have huge effects on resistance. And so they're inversely proportional, right? So once we know Poiseuille's law, we can take that flow equation, right, which is basically taking this pressure equals flow times resistance, isolating for flow on one side, dividing both sides by resistance, we get flow, right, Q equals P over R, all right? So since I have pressure on the top still, and now I have resistance on the bottom, flow is inversely proportional to resistance. If I increase resistance, flow goes down. If I decrease resistance, flow goes up. For pressure and flow, they're directly correlated. If I increase the pressure difference, flow goes up, and if I decrease that, flow goes down. So if I want to put that into a real physiological formula, I can take the resistance from here, Poiseuille's law, 8L times N over R to the fourth, and replace it down here for the flow equation on the right side. But notice R's on the top on the left side, R's on the bottom on the right side. So what I have to do to make this equivalent is I have to flip-flop Poiseuille's law. So that's why flow equals P times R to the fourth, small r to the fourth, over 8L times N. So it tells us that if I increase the pressure difference, flow goes up. If I increase the radius, flow goes up. If I increase the length, because it's on the bottom, flow goes down. And if I increase the viscosity, flow goes down. And using this equation becomes, important in some ways. But, what's the main point of this equation? Well, it's really flow is dependent upon the radius, right? So as an example, anybody want to guess how much, if you went out and ran today, how much blood flow changes to your, how much does blood flow change to your legs if you went running? Anybody want to guess? How much more blood do you need to your legs if you're running? I'll say just jogging.
I think you said 6 times.
Yeah, 6 leads.
Okay, so let's go 6 times, all right? So if it goes 6 times, I don't know why I got rid of that. I could keep it up. So if it goes 6 times, right, and I want to increase flow 6 times to my legs, right, let's look at the way I can do this with this equation, right? What would pressure have to change to increase flow 6 times?
Times 6.
Times 6, right? So that means your mean arterial pressure literally would have to go from an average of 90, right, to 540. Do you think your mean arterial pressure is going to get to 540 millimeters of mercury?
No.
No, right? We worry about it when it gets to 140, right? Mean arterial pressure 100, you worry about it, right? That would be somebody who's got hypertension. So you can't do that. Your head would literally explode before that happened, right? What about length, right? Can you change length appreciably? No, can't. That's not going to do anything. What about viscosity? Can you make your blood 6 times less thick?
No.
No, right? You can't do that either, right? So the only thing you can really change is that radius. And how much do I need to change the radius to increase blood flow 6 times? Well, if I double the radius, let's make the math easy, right? That's 2 to the 4th power. So that's 2 times 2 times 2 times 2. That's 16 times, right? So I don't even need to double the radius. I need to just increase it a little bit because of the 4th power. I'll be able to increase blood flow 6 times to my legs in that case. And so that's really the main determinant of blood flow is the radius. And so all those things that affect the radius of a blood vessel is what really determines blood flow in our body.
So in this case, if you were to give us, let's say, that problem during the lecture exam, and you told us, okay, you're running, you want to increase the flow to your legs. So then the only thing we would have to change would be the radius. And that's
Yep,
it?
and you would increase the radius, exactly.
Yeah.
And nothing else can really change, for the most part. So that's exactly the answer, all right? And just to kind of, here's another kind of freebie. This won't be exactly free, but you should be able to figure out what I'm talking about. A couple people, let me see. One of which I can still see online here, asked about the numbers of things, okay? So had we had the lecture exam in class like normal, I would have had a matching section, and it would have been similar to the one we had last time, but because it just makes more sense to do multiple choice, I had a whole bunch of multiple choice questions with the same answers, okay? And so I posted what the answers are for, I think it's probably 8 or 10 questions about the numbers of things, all right? So as an example, the answers that I gave were 1 or 1.5, 2 or 2.5, 3 or 3.5, 4 or 4.5, 5 or 5.5, and more than 10. All right. So if I said, oh, what's the coefficient for length in Poiseuille's law, right? What would the number be?
8.
8, right? Now, if you look at those answers, and I went through them pretty quick and you're not looking at them, you would notice that there's nothing between 5.5 and 10. So I couldn't ask that, right?
Hmm.
But notice on Poiseuille's law, there is a number I could ask.
4.
And how would you define 4?
The radius to the what power is the radius, or
Perfect. So that would be a good example of, that type of question I would ask in that set is what's the power the radius is raised to for Poiseuille's law, right? So it'd be 4 or 4.5 because it raised to 4.
Hmm.
So start, paying attention to those types of things as we go, as you start, look at studying and things like that.
Can you put that question on there?
Well, there are other questions similar, right? And maybe that one, it depends on the luck of the draw, whether you get that one or not. But I would think that would potentially be on there. One of the other things that people ask, and again, it's just a few of you, but I'll clarify. Because a number of people's schedules have changed where you're not available at normal class time anymore, especially for a number of you that work in the medical field where, it seems like they're working you hard. Or I have, one of your classmates got a job with Amazon or something because they lost their job, and I don't know what they're doing, but they're working crazy hours. So what I've done for the exams, and I'll do this for the rest of the exams, the rest of the semester, is you still have to take it on a particular day, right? But I'm allowing you, if you're the 8 a.m. class, I'm not making you get up at 8 and take it at 8. You just have to take it on Monday. And since everybody would have taken the exam on Monday, whether you're in the morning or night class or the Tuesday, Thursday lab class, everybody would take it on Monday. So that one part online has to be done Monday, right? But I'm allowing you to turn the take-home part, in this case, the 4 essay questions in as late as Tuesday. So if you want a little extra time.
Thank you. Appreciate it.
We'll do the same thing for the lab quiz we did this time, where it'll be available Wednesday and Thursday for people that would be in the Tuesday, Thursday class till noon. That caused some confusion for some people, but I think they got it now. And then we'll do the same thing, and I'll try to make the questions for lab 4 available early like I did this time. So if you haven't looked or paid attention, and I'm guessing you all have because you're here, I already made the essay questions available online, so you can look at the assignment for the lecture exam 3 for the take-home part, and you can already see the questions. That might, and just look at it again, and I haven't talked about this a lot online and probably could have talked about it more, But one of your jobs as a student is to figure out how to study for particular classes. And I think you all intuitively understand that. But, you know, think about it, and that's kind of what that first homework was designed to do. Think about, okay, if you were in the instructor and doing this, and it's okay, here's the questions I have for this part of the exam. Do you think this exact same essay questions, concept type things would appear on the other part of the exam? They're important, but I've already sort of asked them, right? And there's certainly, you know, multiple choice questions I could ask around them, but, you know, you're not going to see, you know, any essay questions on the exam tomorrow that you have to take. It's all multiple choice, right? So just kind of know that going in, and it tells you some of the important things. And, you know, as an example, you know, one of the questions asked about the homeostatic control of mean arterial pressure, right? And certainly there will be questions on the multiple choice, because I thought that was important. As a matter of fact, if I asked one question out of this section, that would be it. So, you know, pay attention to the multiple choice, you know, what multiple choice type of questions I could ask as you go through that, right?
I have a question. Sorry, going back to the review. There was a section that said the mean arterial pressure is homeostatically regulated, and you gave all the different intrinsic and extrinsic factors for heart rate, stroke volume. What was the other one? The
TPR, total peripheral resistance.
Yeah. So, and a lot of the times you would say strength, but like, oh, you increase the volume, then you increase the stretch, then you increase the strength. When you say strength, do you mean the stroke volume?
Yeah, so this is the relationship, right? The harder you squeeze the heart, the more blood that's going to come out. So if I increase the strength of contraction, I'm going to get a bigger stroke volume.
Okay, so every time you would say strength is stroke volume. Okay.
Yeah, so when we're talking about strength, we're talking about stroke volume. If we're talking about radius or diameter, right, we're talking about total peripheral resistance, right? And if we're talking about rate, some sort of rate, right, we're talking about heart rate, obviously.
Okay.
Okay, so I have a question on total peripheral resistance. Intrinsically controlled through myogenic autoregulation, which is saying that arterioles change their own diameter in response to stretch or pressure.
Mm-hmm.
So if there's more pressure, do they constrict?
In this case, they dilate in a systemic blood vessel.
And so if there's less pressure, they dilate too?
No, they go the other way.
Oh. Okay, can you explain that? So if there's more pressure, then the arterioles dilate?
The
Okay,
stretch,
so let's.
stretch, no?
So for the myogenic mechanism, right? We'll put it up. So the myogenic mechanism, if we increase pressure, right, then what we're trying to do is we're trying to maintain a constant flow, right? So if we have more pressure in a vessel, that's going to increase the stretch of the vessel. Does that make sense?
Yeah.
As I'm trying to put more blood into this relatively floppy vessel, it's going to stretch more, okay? If I stretched more and I left it stretched, what's going to happen to the diameter?
It's going to increase?
It's going to increase. What's going to happen to flow?
Increase?
It's going to increase. I don't want that flow to increase. So if it pushes on the outside of the vessel pushes back on it. Does that make sense? And tries to maintain the same radius so that constant flow happens. So you're trying to make up for the change in pressure by changing the radius of the vessel to keep flow the same.
And that's the elasticity that makes up for it, right?
It's for that, it's not so much the elasticity, it's the muscles. So that's why it's called the myogenic mechanism, myo referring to muscle, genic referring to where it comes from. So the muscles can constrict or dilate all by themselves based on that stretch or pressure within the blood vessel itself. And again, if you just think to maintain constant flow, if the pressure goes up, then I'm going to constrict the blood vessel to offset that.
Okay, so the myogenic autoregulation is something that our body has in place to maintain constant flow?
Yes.
Okay.
Oh,
And
yeah.
so increasing the pressure increases the stretch of the vessels, which makes them bigger, right? It would cause them to dilate?
Well, it makes them bigger, but we don't want them to get bigger because that would increase the diameter, so we constrict them in response to that.
I see. Okay. I think it's like the way the slide was written that I just was a little confused. So because it stretches, the muscles then kick in to constrict.
Restrict it from overstretching. Yeah.
Oh,
Okay.
is that the outer regulation? Once it stretches, the vessels like outer regulate and
Exactly.
Okay.
And it comes from, that's why it's called the myogenic, it comes from the muscles itself. And they've done studies where they literally stripped everything out of an arterial except for muscles, and it still happens. So it comes from the muscle, that's why it's called myogenic.
Oh, got it. I was actually confused about that too.
Can I ask you about the ventricular performance, like what EDV and ESV is?
Mm-hmm.
And ejection fraction, like just that little section.
Okay, before, there's one thing I want to say. Okay,
Okay.
let's see where I got. I'm trying to find the slide that I want. I'll go here. So I never really, I don't think, answered one of Jess's original questions. So when we'll start here. So when we look at the, what did you just ask about? The
Me?
SV, EDV stuff, right?
Yes.
That would be appropriate here anyway, so we'll come back to this in a second. But let's start with just cardiac output right now, okay? Now, cardiac output, some people just do C capital O. That causes problems because we also talked about carbon monoxide in this section, which, how do you abbreviate it?
CL.
Capital C, capital O, right? So some people use Q, which then confuses stuff because now we've used Q as a general flow, right? And now Q would be a very specific flow. And so, you know, I've never seen anybody come up with a good symbol that was consistent that people use for cardiac output. But cardiac output, how would you define that? Not formulaically, but how would you define it, you know, textually? What would you, somebody said, define cardiac output. What is it?
How much blood your heart pumps per minute?
Perfect. Okay. So how do we get to cardiac output is you take stroke volume and heart rate and multiply them together. Okay.
Mm-hmm.
If it's how much blood your heart pumps out in a given amount of time, then it's a blood flow. Does that make sense? It really is the blood flow out of the heart, right? So if I go to this slide, it's okay. Pressure equals flow times resistance, right? That's our general equation. If we take a specific pressure, mean arterial pressure, equals a specific flow, cardiac output, the flow of blood out of the heart, times a specific resistance, the resistance of the, to flow basically in the body. We've just taken this general P equals QR equation and made the specific mean arterial pressure equals cardiac output times TPR, or the way we do it, because we want to look at the individual components of cardiac output, stroke volume times heart rate times TPR. So it still follows this general pressure equals flow times resistance. We just have a specific pressure we call mean arterial pressure times the specific flow we call cardiac output times the specific resistance we call TPR.
In the video, you said that we would use like kind of like choose whatever mean arterial pressure formula, depending on whatever information we were given. So this is one of the cases, right? So if we are only given the systolic and diastolic, we're not even going to look at this. But if we're given the, let's say, oh, this is the stroke volume and this is the total peripheral resistance and this is the heart rate, then we would use that.
Use that formula, yeah. Exactly.
I have a question on this slide. So mean arterial pressure is unaffected by exercise?
Yes. It doesn't change much when you exercise. And as a matter of fact, if you're doing, like if you're medically doing a stress test on somebody, mean arterial pressure changes by more than 10 millimeters of mercury, you're supposed to stop the test because it's dangerous, whether it goes up or down.
Okay.
Right? And so, you know, and the whole point of that bottom part, let's finish the idea, is what's going to happen to cardiac output when you exercise? Does your heart rate go up?
Yeah.
Absolutely.
Yeah.
You think your heart pumps more blood?
Yeah.
Absolutely. So to compensate for the increase in heart rate and stroke volume, what actually has to go down then is what?
Then the resistance.
Resistance, right? So you get a lot of vasodilation in your muscles and resistance goes way down and your mean arterial pressure really doesn't change much when you exercise.
I see. Okay. So because the vessels dilate in the muscles, that is how the mean arterial pressure overall isn't affected by exercise.
Exactly. Even though the heart rate and stroke volume go up significantly, right? I mean, you know, if you look, we didn't do it, right? But the magic formula for maximum heart rate is 220 minus your age, right? So, you know, make math easy. A 20-year-old, you know, college female would have a max heart rate of 200. And if they had a resting heart rate of, you know, 70, right, their heart rate would increase almost 3 times at maximum. And so just without worrying about stroke volume changes, then TPR would have to do what? Go down 3 times to offset that. Does it make sense?
Yep.
Okay. I did have another question. It's all in this section.
Okay.
It is about, well, it's about the baroreceptor reflex arc and how that has short-term, it opposes changes to mean arterial pressure in the short term, and it's with the kidney. So I understand the sympathetic risk, like if you increase the pressure by 10 millimeters of mercury, then the response would be to bring it back down by 10 millimeters of mercury. And so in the kidneys, decreasing sympathetic activity in the kidneys, that causes a decrease of blood volume?
Yes.
How?
We'll talk about it when we get to the kidneys, but it has to do with
I knew you were going to say that.
well, it has to do with the constriction of the afferent and the efferent arteriole. And the afferent is affected more. That's the one that leads to the filter. So if you dilate that, you'll get more blood into the filtering capillary called the glomerulus. If I have more blood there, there'll be more pressure. And since I have more pressure, I'll push more fluid out that will become urine.
Okay.
So basically, right, and one of the things we're finding, when I was in school, I was taught, you know, a little differently, that the baroreceptor reflex was the second-to-second, minute-to-minute, short-term regulation of blood pressure, and that the blood volume was the long-term regulation. And now we're finding that the more recent stuff says, no, the kidneys are really important short-term as well through this process that I didn't really explain, but sort of did.
I had a feeling that you were going to explain it more in the kidney section. Sometimes when it doesn't, it's hard for me to fully grasp it if I don't have all of it. Like I can just basically accept it as a fact that you told us and that we should know, but I don't fully understand it until I know why it happens.
So here, and it gets back to this idea. I kind of mentioned earlier that we can't differentially stimulate the sympathetic system to different parts of our bodies, right? I mean, if I stimulate the sympathetic system, as you kind of see in the baroreceptor reflex one, it's going to go to everywhere and decrease. But in your kidney, you have, it's an example of, and just a little quiz for you guys. What do you call that? Those special systems in your blood vessels where you have two capillary beds in series, one after another?
Portal system.
Portal systems, right? So your kidney is an example of a portal system where you have a capillary bed in one and then a capillary bed later on. The first capillary bed in the kidney is the actual filter. And so it's the only place in the body where we have an arterial bed, a capillary, an arterial, and then another capillary. The other portal systems don't have arterioles in between the two capillaries. So both are going to have sympathetic stimulation. And if I increase the sympathetic stimulation, I'm going to squeeze the one that goes to the filter. I'm going to squeeze the one that comes from the filter. And squeezing both sides the same way isn't going to allow me to change anything. So that creates a little bit of an issue. So what our body's done to compensate for that is it's put more receptors. Remember, it's the receptor that gives the action anyway, right, from Cannon's postulates. It's put more receptors in the first arteriole, called the afferent arteriole. So when I stimulate the sympathetic system, it's going to affect that one the most. And so that's going to change blood flow through the filtration apparatus, which is going to change how much fluid gets filtered. And you could probably, surmise, although it's not as direct as you would think, that the more fluid that gets filtered, right, the more urine I'm going to make. And so it changes the filtration aspect of it by changing the sympathetic system.
Okay.
But we'll see it more in the kidney. As a matter of fact, in the kidney, we'll talk about homeostatic regulation of something called GFR, the glomerular filtration rate. And one of those will literally be that sympathetic stimulation. All right, so one of the things I want to look at, that was asked by J-Raz iPhone, was the numbers. Where was that? Oh, it's on the cardiac cycle. I'm looking for the systolic, diastolic stuff.
It's under pressure flow resistance, part 4.
Yeah, I thought we had more numbers than that. Well, some of it might be on this. So, a couple things that you should get out of the cardiac cycle is, and a good place to look at how to deal with this would be the 5th group problem. So the group problem answers are posted, and I did a video for each one. So look at the 5th one. That would be in the 2nd video. Obviously, you should watch them all, though. I think they would help. But the end diastolic volume, right, is the volume of blood in the ventricles at the end of diastole, okay? To make our life easy, we're going to assume it's 100 mLs, although most people are probably higher. Obviously, it depends on body size and a number of other factors, but we're going to assume 100 mLs is not a bad number. So that's the amount of blood, the EDV, end diastolic volume, that you have in the ventricle. That's the amount of blood that's available to pump, basically, okay? So when I pump blood out of the heart, right, during ejection. I don't pump it all, as we mentioned before, and there's an amount left. The amount that's left is called the end systolic volume, or ESV. And that's the volume of blood in the ventricle at the end of systole, or at the end of a contraction. That's highly regulated as well, and that's regulated by the two intrinsic mechanisms we talked about for the control of stroke volume. The Frank-Starling, which deals with the volume of the heart before ejection, so the end diastolic volume, and the preload, which is the pressure of the heart before ejection, right? And so that number is highly regulated, for most people about 30 mils. So if we started with 100 and our end diastolic volume was 100, and we ended with 30, our end systolic volume was 30, that means we had to pump out the difference of that, right? And so the difference would be the stroke volume, right? So end diastolic volume minus end systolic volume gives us stroke volume. And so that was one of the important numbers that we looked at in terms of pressure. And then from that, we could use other numbers. So my stroke volume equation right here, right? End diastolic volume minus end systolic volume, the stroke volume. Other equations that's kind of related. And I don't know if any of you deal with this, because I know some of you work in the medical field with ejection fractions, but ejection fractions an important component of people that have potential heart issues. An ejection fraction is how much blood do you pump out over the available amount of blood, what percentage, right? And so the amount of blood you pump out is the stroke volume. The amount of blood you started with is the end diastolic volume. So your ejection fraction is stroke volume divided by the end diastolic volume times 100. And so again, using normal numbers, right? If end diastolic volume, looking at the top equation, was 100, and end systolic volume was 30, that means stroke volume would be 70. So ejection fraction, I get 70 over 100 times 100. So my ejection fraction normally is 70%. Someone who has cardiovascular problems, like had a heart attack, their ejection fraction might go down to 25 or 30%, and certainly be a problem. So those numbers are good to know, and that problem again, number 5, I think really helps show that in the group problems.
Can I ask about problem number 5?
Mm-hmm.
So in it, you said that it was basically like the person can die from a heart attack and still have oxygen in the chambers because the heart gets its oxygen through the coronary arteries. Is that
Yeah. Mm-hmm.
okay? And so where do the coronary arteries like return the blood to the, does the blood go back to the left atria, the right atria?
So if you remember, the first branches off the aorta, right, are the branches that go to the coronary circulation, right? And if you think back to anatomy, you have the different, I don't know if I have a front view of the heart, I probably do somewhere. So looking here at the heart, which shows some of the coronary arteries, right? The coronary arteries go to what they technically call cardiac veins, and the cardiac veins all eventually go back to the right atrium to what they call the coronary sinus, right? If you remember that, and the coronary sinus dumps blood back into the right atrium. So and you can't even see the branches for the coronary arteries off the aorta, right? They're actually way down here. And so those provide the oxygen to the heart, and then it's the blood vessels. And this is a terrible picture because, like the big one right here should be the left anterior descending artery, and that's the one that, if you had Dr. Dixon, she always talks about the widowmaker and how serious, because that provides most of the blood to the left ventricle, if you block that coronary artery, you're going to die. And that's why some people die from a heart attack and some people don't, is what blood vessel gets blocked and what's the cessation of blood flow. Because as humans, we have no ability, and that's the whole point of that question, to extract oxygen from the chambers. We have to get our oxygen from, because our heart walls are so thick, from the coronary circulation. So it doesn't matter, there's 100% oxygen in your left ventricle. If you're not getting it to the coronary vessels, you're not going to live.
Okay. So, because then you said that heart attacks usually result from someone having an occluded vessel. And are you talking about an occluded coronary artery or
Yes.
coronary vein?
It would be coronary artery.
Okay.
Yeah. Your veins.
And so wait, but if that's occluded, then they wouldn't be able to get oxygen.
Exactly, and that's what would cause
which is
the
what
heart
causes them to die? Is that?
Yep. Because
That's okay. And so they can have a heart attack, but not because that one got occluded, because a different one got occluded.
Yeah, you've got a whole bunch of coronary arteries.
Okay.
And not all of them are going to have necessarily a blockage at the same time.
Okay. Gotcha.
Right? And
I think I was just a little confused because when I was watching the group problem video, you were saying like, oh, well, the coronary arteries give the heart its oxygen. And then like a minute later, you were like, and people die from heart attacks from their coronary arteries being occluded. And so but I understand it now.
Yeah, so just kind of look at it this way. I probably need to find another famous person because you don't see him as much anymore. I guess he's done some Netflix specials recently, but David Letterman, right? A number of years ago, he had a quintuple bypass.
Oh,
He took 5 vessels from other parts of his body and bypassed narrow coronary arteries before they blocked up and gave him a heart attack, right? So that's what they do. They literally sew in an extra blood vessel to bypass that area where it's got, the occluded. You can occlude other blood vessels in the body. If that happens to your brain, that's what's going to cause a stroke, right? Or at least 80% of strokes. 80% of strokes are what they call ischemic strokes, and that's because you get an occlusion, just like you would in your coronary blood vessel, to a vessel to your brain. 20% of strokes are what they call hemorrhagic, where you're actually bleeding in some vessel in your brain. Those are much more serious, although all strokes are fairly serious. Or it could happen even in your legs. That's causes a clinical condition called claudication. But the idea is people's legs hurt because they can't get good blood flow. And as an example, you see diabetics with that, and they'll get like a diabetic ulcer in their foot because they don't have good blood flow, and they got a cut and it never heals, right? And that's, if they can't fix it, then eventually they're going to end up amputating the foot. And that's the number one reason we see amputations in our society nowadays, is people that have that. So it can happen anywhere, but look at it from a metabolic standpoint. Your heart typically has about 20 minutes of anaerobic metabolism that it can have until heart muscle starts to die. And so if you have a heart attack and you get a cessation of blood flow to a certain part of the heart, you're going to lose that heart muscle if you don't get the oxygen to that area within 20 minutes. And so becomes a really big deal, obviously, to do that. And I don't know if it still is, but John Muir Concord, right?
Concord, yeah.
Yeah, spent a ton of money on their big, heart cath stuff, right? And I think their goal is to get people in there like within 14 minutes. It used to be, I don't know, they might have shortened it now, to try to make sure they get the blood flow flowing so that the recovery rate is significantly better. Right. So in your brain, you got about 4 or 5 minutes probably where your brain can go without oxygen before you have irreversible damage. And your brain and your heart muscle aren't going to regenerate. And if you lose that tissue, you're not going to be able to use it anymore. So that's why strokes and heart attacks are so serious, where other places aren't as life-threatening, although certainly serious.
Okay.
What else?
I think those were all of my questions.
All right. Anybody else?
No, Jessica, you had really good questions.
Oh, thanks.
She always has good questions.
Well, I'm just so fascinated by it. Like, yeah, that's it. I'm just so fascinated by the body.
All right.
Mm-hmm.
All right. So, again, don't forget to do the one online tomorrow, and then make sure you get the other one in by Tuesday night. And then we'll just keep rolling. I haven't posted them on Canvas yet because I didn't want people to worry about them. But I've got a couple videos up for lab. Your next lab quiz isn't too far away. It's like the first Wednesday in May or something. Not that far away. So we'll just keep rolling.
Hey, did you happen to hear, are they offering microbio over the summer yet, or they still haven't decided?
Things have changed so much. And what I originally heard, which you're not going to be happy with, was, it's weird because they said, and I don't know if I'm supposed to say anything, so you didn't hear it from me,
Okay.
but the fall classes are all going to be either strictly online or potentially hybrid, but no true face-to-face courses. So there may be a situation where students will come to school for either some exams or some select laboratories, right? Like as an example, the micro instructors, which makes total sense to me, have a problem with you receiving credit for a micro class, yet never touched a microscope.
Yeah.
And so they're trying to get this hybrid stuff on, but it really depends on what happens with the virus and social distancing and everything else. And, it really comes down to the philosophy about what we're trying to do about it. Originally, the social isolation was to flatten the curve, right? It wasn't to stop the spread of the virus. It was just to make sure not as many people got sick at the same time. But right now, it seems to have changed more towards preventing the transmission of the virus at all.
Yeah,
And
I have actually noticed that in the last couple of weeks as far as the talk around it.
About it, right?
Yeah.
So it depends on where, it's largely up to the state and the county, and obviously the community college district's going to do what they want to do with that. Ideally, we would have the ability to do some classes, but how can you do them safely and question some of the different things? But so it looks like I am planning on doing physiology all online in the fall, literally, just like we're doing now. Changing some things and trying to learn from this experience and make it hopefully better. But, if you want to take it in the fall, you're probably going completely online. And so originally the micro people said, well, we're not going to teach completely online in the summer if we have to. And they haven't made that decision yet as a district, whether we have to go there. And they still had it open for face-to-face or hybrid classes, which doesn't make any sense to me because they said the fall is not going to be any face-to-face classes like normal. So that to me means the summer can't do that either because it's earlier, not later. But they haven't stated that specifically. But my feeling is that nobody's made a decision yet, because if they have to go online for micro, all of it in the fall, if they want to teach it, then maybe they'll do it in the summer too. You know what I mean?
Yeah.
So, but
Great.
the last I heard from my department, right, was if they can't teach face-to-face, they're not going to offer it. But that was before they came out and said, in the fall, you're not going to teach face-to-face. So,
Man. Sorry, the fall's supposed to be my last semester.
I know, me too. What the
Yeah,
heck? Oh my god.
we had a meeting Friday and I argued, there are students that have planned their schedule that are waiting for that. And I understand that if you can't get it up and running, right, but you're going to have to do it in the fall anyway. So, I don't know. It's not the best of situations, right? But I think it's the best course of action given what we're stuck with. If that makes sense.
Yeah. Yeah.
Sometimes there's no great decision or even good decision, but there's often a better decision.
Right.
And that's what I was arguing for. But I don't teach it, so I can't teach it. Matter of fact, I actually told them, hey, if you're not going to teach micro, because they on schedule had 2 146s scheduled originally. And so there were 2 different instructors for each class. And so I'm not sure how much those people, A, need money, right? Because if you don't teach in the summer, you don't make money. And B, if you already know, hey, whatever I make in the summer, I could use in the fall or most of it, then maybe I'll teach. So I don't think that decision's actually been made by those people yet. And there still hasn't been a decision yet to say we're not doing at least a hybrid over the summer. So,
Okay.
and that literally, I hate to tell you this, as far as I know, is not going to be probably made till June.
Yeah. All right.
And if they do offer the summer courses, if it's a hybrid, it would start on July 6th and go through the middle of August.
Okay.
But my
Hopefully
guess,
they start the fall later then. Shoot.
yes, and the fall will start a week later, unfortunately. So there won't be a whole lot of turnaround time. So enjoy if you're hoping and it happens, enjoy your time between, in June.
Yeah.
Enjoy your June.
Okay, thank you. I appreciate
Thank you.
transparency and that you always give us as much information as you have. 'Cause I think this is stressful for everyone.
No, I get it. Yeah, I understand that. As a matter of fact, I told them I'll teach physio over the summer if online if you guys don't teach micro. So who knows? Not that you need physio again, but
Yeah.
but just because I think it's important. It's not necessarily the easiest thing for me to do, but I think it's the best thing to do for students. And as an example, I didn't know this until I looked at the schedule for another reason. They plan to offer between DVC and SRC literally seven 139 courses. So they'll have 7 anatomies, and we'll teach no 140. So all the students that got done with anatomy this semester, which they have between SRC and DVC 14 sections, we only have 10 of physiology. There's going to be all those students that need physio probably, and all the students from the summer, and it's just ridiculous. So I said we should teach them over the summer, but I got some feedback from the dean about how we shouldn't do that, but well, we got to do what's best for the students. So we'll see.
All right, guys, I'm gonna leave the meeting.
Same
All
here.
right, I'm going to end it anyway, so everybody's leaving.
Okay. All right.
So
Thank you,
email me
everyone.
any
Thank you.
questions. We'll see you
Okay.
later.
Bye.
Okay. Thank you, Professor. Bye.
See ya.